Now let's look at an Excel example of hypothesis testing for single population variance or standard deviation. So you can set up the hypothesis in any one of these three forms as we have already discussed, and the test statistic is given by this formula with n-1 as the degrees of freedom. So now let's look at an example. Here in this example we have a metro bus company that wants to promote an image of reliability of service, and one of the aspects of reliability of service is to maintain your schedule as published. So the variance of arrival times, the variance of departure times, you want to keep that variance as small as possible. So here in this example we want to test. In this example, we want to test whether the variance of bus timing is greater than 4. We want to keep it less than or equal to 4, but if it is greater than 4, then we want to check that and consider that as excessive variance in bus times. So this is what we want to test, and we have a sample information given here. We take a sample of 24 bus arrivals, and the sample variance turned out to be 4.9, and then we want to do the test based on that. So let's define. So now let's define the parameters and set up the hypothesis and do the test. So here our population is arrival times, sigma squared is variance of arrival times, then we have the sample size and the sample standard deviation. Okay, so we have defined the parameters. Now we want to test what? We want to test whether the alternative hypothesis, the variance is greater than 4 minutes. So the null hypothesis will be less than or equal to, the alpha value is 5%. So let's move the alpha value down here. So we will have the value of alpha in a single cell. Okay, now we are given that sample size is 24 and the sample variance is 4.9. So the test statistic value is given by this formula. Okay, so you need to be very careful in terms of whether we need to square or not. If the variances are given, then you don't need to square because it is already squared. But if the information is stated as standard deviation, then we need to square these numbers, B37 squared and B32 squared. But here we don't square it because these are already squared values. Alright, so that's your test statistic. n-1 is the. Okay, now let's do the test. We will use both the chi-square table value approach and the p-value approach. And here, to set up your chi-square table value, you need to look at the alternative hypothesis. And since this is greater than, we need to use the right hand side chi-squared value. So that will be chi-squared.inv.rt. If it was the left side, then you would use chi-squared.inv. So probability is alpha. This is a one-tail test, so we don't do alpha over 2. It's just alpha. And degrees of freedom. So that's our table value. And if the chi-squared calculated value, if it is greater than the table value, then we will reject, otherwise we will not. So the conclusion is, since our chi-squared calc is less than the threshold value, chi-squared table value, we cannot reject the null hypothesis. Okay, now let's look at the p-value approach. So now the p-value is the right hand side tail value. So the right hand side tail is we can use chi-squared dist.rt. So the rt function is the right hand side function. So here we use the test statistic, comma, the degrees of freedom. So that will give us the p-value for the test. So and that is the p-value. So the right hand side tail is the p-value. So the conclusion is same as before. Since the p-value is greater than alpha, we cannot reject the null hypothesis. And now we need to do an interpretation. So we do not have sufficient evidence to conclude that the variance is greater than 4. And if we did conclude it was greater than 4, the probability of type 1 error will be 20.9%. So there is the interpretation.